Hello class, this lecture is lecture 5C, cation exchange capacity. In this lecture we'll define cation exchange capacity and explain the principles that govern it. We'll explain how cations impact flocculation and dispersion, describe how CEC and ECEC are measured, estimate CEC based on soil properties, and define anion exchange capacity and explain the principles that govern it. So the cations and anions in our soil, there's a whole bunch of them, but the primary ones for cations we have hydrogen as H plus, ammonium NH4 plus, potassium as K plus, magnesium Mg2 plus, and calcium Ca2 plus. For anions we have chloride Cl minus, nitrate NO3 minus, sulfate SO4 2 minus, and phosphate PO4 3 minus. So we have, of all the cations and anions present, those are the predominantly the ones that we see. The last slide has to be reversible, and it has to have a charge equivalence. The cations also have to follow what we call the ratio law, and that means that the total amount of cations that are in the soil, whether they're absorbed or in solution, those are going to reach an equilibrium so that the total amount is reflected on the total amount that's absorbed. And so what I mean by that is here we have 20 calciums that are absorbed onto a colloid, and we have 5 milligrams or 5 magnesiums, excuse me, that are in solution. Now, right at this moment, these are not in equilibrium because all the calcium is absorbed and all the magnesium is floating around in solution. And so eventually what will happen is we'll reach an equilibrium where if you think about all these cations, there's about a 4-to-1 ratio going on here. And so so what we end up with is we have calcium and magnesium. So we'll have some of the calcium being exchanged with the magnesium, and we're still keeping the same balance. And actually this slide is missing the calcium, so it should be 4 calciums that are going off into the solution here. But we end up with the same ratio in total, but what's reflected in the solution and what's reflected in what's absorbed are equivalent in terms of the proportions of calcium and magnesium. So it maintains that ratio. There's also this concept of cation selectivity. So these cations will be bound to the colloids according to this pecking order that you see here. So the one that bonds the strongest is aluminum. So aluminum is a trivalent cation, so it has 3 plus charges, and it's also very small. So it does a good job of holding on tightly to the cation exchange sites. And next is calcium, and then magnesium, and then potassium. And potassium is more or less equal to ammonium. And then we have sodium and hydrogens at the bottom. So we have this pecking order of which ones form the strongest bond with the exchange sites in the soil. So generally what occurs is the small cations with a higher valence are held on the tightest. And cations that are larger with a low valence are held loosely. So sodium is one of the biggest cations present or on this list, and only has a 1 plus charge, so it's monovalent. And so sodium is held on very loosely, whereas aluminum is very small and it has a 3 plus charge. So that's really what kind of establishes this here from the previous slide. So going with the next term, let's formally define this term cation exchange capacity. So cation exchange capacity is the total amount of cations that can be absorbed on a given amount of soil, and this is usually expressed in terms of the amount of charge that's on the CEC, the amount of charge per unit mass of soil. And so one of the recommended textbooks for this class, it that book describes this as the number of centimoles of charge, usually expressed as centimole sub C, and C, the sub C means charge. So centimoles of charge that can be absorbed per unit mass. And usually a common unit is centimole of charge per kilogram. So we have kilogram raised to the -1. So that's the same as taking centimole of charge divided by kilogram. So centimole of charge per kilogram. And another common unit that's used is milliequivalents per 100 grams. And I just want to note that 1 centimole of charge per kilogram, if you do all the conversions, it's equivalent to 1 milliequivalent per 100 grams. So these are the two units that we use. So centimole of charge or milliequivalent. And 1 is taken per kilogram, 1 is taken per 100 grams. All right, so CEC is measured using a buffered solution, and it's buffered to a pH of 7. Sorry, my animations are going a little bit crazy here. Now I want you to go ahead and just think about this here. So we have 2.4 grams of ammonium and 100 grams of soil. So I want you to calculate this on your own, but I'll walk you through the steps. So if we start off with grams, if we determine the molecular weight of ammonium, we can convert from grams of ammonium to moles of ammonium. Once we have moles, we can divide that by 100 to get to centimoles. So centi, just like centimeter, there's 100 centimeters in a meter. There's 100 centimoles in a mole. So use the molecular weight of ammonium to go from 2.4 grams of ammonium to moles of ammonium. Divide by 100 to get centimoles of ammonium, and then and that would be our centimole of charge, because for every 1 centimole of ammonium, we have 1 centimole of charge. We get to take our centimole of charge per 100 grams of soil, and that is our CEC. So I want you to go ahead and do that calculation on your own. All right, now, or pause the video and do it on your own. Now I'm going to walk you through the actual calculation here. All right, so 2.4 grams of ammonium. And if we calculate the molecular weight of ammonium, it's 18 grams per mole, or 1 mole per 18 grams. And so if we set it up where there's grams here, then we have grams of ammonium on the bottom and moles of ammonium on top, the grams of ammonium cancels, and we're left with moles. And so 2.4 divided by 18, we get 0.133 mole of ammonium. And we want to convert that to moles of charge. So 0.133 moles of ammonium, and we know because it's a monovalent cation, for every mole of charge we have 1 mole of ammonium. So we have 0.133 moles of charge. Converting that to centimoles of charge, we have 0.133 moles of charge, and we get 100 centimoles of charge for every mole of charge, and we get 13.3 centimoles. And I think I misspoke earlier when I said divide by 100. We need to multiply by 100. So we went from 0.133 moles of charge times 100 centimoles of charge per mole of charge. We get 13.3 centimoles of charge. And now we have centimole of charge per gram of soil, per 100 grams of soil. And we want to have it in units of centimole of charge per kilogram. And so we can take 100 grams times 1,000 grams per kilogram to convert it to kilograms, and we end up with 133 centimole of charge per kilogram of soil. So for this particular example, that is the calculation for the CEC in that example soil. It's on the higher end, but that's how we would calculate it. More note on that map. Notice in this part of Nebraska, that's the Sandhills region. So sand has very low amounts of CEC, and that shows up on the map. So 0.1 or 1.8 to 3.6 for the sandhill region. So that's kind of interesting. All right, so we walked you through the laboratory method for calculating CEC. There's also a way that we can estimate CEC based on some known soil properties. So say we farm a field and it has mollisol soils, and it's an area known to have 2-to-1 mineralogy, so vermiculite and smectites. We know that the clay content is 25% and the organic matter content is 5%, and it's been limed to a pH of 7. So let's do some sort of back of the envelope calculations to estimate the CEC. So if we have 1 kilogram of soil, the CEC from organic matter, so organic matter we have, we can assume that it's 200 centimole charge per kilogram, and so if we have a 5% of our kilogram of soil is organic matter, then we can take 0.05, so the decimal form of 5%, times 200 centimole charge, and we get 10 centimole charge per kilogram of soil from that organic matter. And then what we get from clay, we have 25%, so 0.25 times, and this 125 centimole charge per kilogram is what I'm getting as the average of vermiculite and smectite. So smectite's 100, vermiculite's 150. We're splitting the difference, and we'll say that clay is around 125 centimole charge per kilogram of clay. And so we have 25% of our soil is that. So 0.25 times 125 centimole charge per kilogram, and we get 32 centimole charge per kilogram of soil. And the last step is add those together. So we have 10 centimole charge per kilogram from the organic matter, 32 centimole of charge per kilogram from the clay, and the total is 42 centimole charge per kilogram. So this is our estimated CEC just based on knowing the organic matter content and the clay content and the clay mineralogy. So CEC is talking about more often, but in some situations the ECEC is more useful. So again, the traditional CEC method is performed at a buffered pH, and that more or less determines the maximum CEC under ideal conditions. So an ideal pH right around 7. Now this is not always representative of field conditions, and so in the field, what can be more useful is the effective cation exchange capacity. So say we have a soil that is almost never limed to a pH of 7. Maybe it's kind of bounces between a pH of 5.5 and 6. So it's always more acidic, or at least slightly acidic. And so it might not be that useful to estimate the CEC at pH 7 because the field is never at that pH. So in that situation, we can use the effective cation exchange capacity, and it's analyzed the same way as the CEC, except that the solutions that are used are unbuffered pHs. So the pH is unbuffered. And this can be more representative of field conditions, so because it's done at the pH that the soil actually exists at. So this is a lot more useful for acid soils. So if you have a field that is rarely limed, or maybe in a country or a part of the country where there is very little liming that occurs, or maybe the soils are just naturally acidic, then ECEC becomes more useful. So for effective cation exchange capacity, what we're really talking about is this figure here. So if we look on the right side, if we have a pH of 7, then we have some cation exchange capacity that comes from the permanent charge from the soil. This permanent charge is the isomorphic substitution that is built into the clays. And then we have some pH dependent charge And then we have pH dependent charge that comes from the organic matter. And so the total, the sum of the permanent charge, the pH dependent charge from clays, and the pH dependent charge from organic matter, the total amount varies as we go from one soil to the next, or as we go from one pH to the next. And so if we're looking at a pH of 7 versus, say, a pH of 5, we're going to have a very big difference in how much CEC actually occurs. And so that's why, in some cases, effective cation exchange is more useful because we're getting a more reasonable assessment of the CEC that the plants and the microbes and the soil in general actually experiences. All right, so we talked about this pH dependent charge in the previous lecture, and so just a reminder, as we increase in pH, most of the exchange sites become deprotonated, leaving a negative charge, and that makes the CEC go up. As we decrease in pH, so going from pH 7 to, say, pH 4, then there's more hydrogen in solution, and the more likely the hydrogen is in solution, or the more amount of hydrogen is in solution, the more protonated the exchange sites are. So there's a hydrogen that's taken the place of these negative charges. And one thing that occurs is at a low pH, we can actually overcompensate from those hydrogens, and we can actually get a net positive charge on a colloid. And so our anion exchange capacity, as we go from a neutral pH to an acidic pH, our anion exchange capacity goes up as we decrease in pH, and it goes down as we increase in pH. CEC is the opposite. So CEC is lowest at a low pH, and CEC is highest at a high pH. So you could say that soil pH and CEC are directly related, whereas soil pH and anion exchange capacity are inversely related. All right, so the next concept is CEC and aggregation. So one thing that I sort of imagine with clays is if you've ever played with magnets, if you have a stack of magnets, if you have them aligned correctly, then they'll all collapse and they'll all kind of stick together. But you have to have a positive side of, or a positively charged magnet in between two negative charged magnets. And as long as that occurs, then those magnets will all collapse and they aggregate. But if you have two very strongly charged negative magnets with a weak positive magnet in the middle, then the attraction of those negative magnets to the positive magnet is less than the repulsion force between those two negative magnets. And so when that happens, those magnets can't be stuck together. They repel. And if you think about clays, that same thing can happen if you think about these colloids and cations as magnets. If we have a lot of small but powerful magnets like aluminum, then that makes these clays aggregate and they stick together. But if we have some big, very low power cations like sodium, then the sodium doesn't allow for enough positive charge to offset the repulsion of those two negatively charged colloids. And so sodium takes up a lot of space, has a very low amount of charge, and as a result, if there's too much sodium, then the sodium can cause the dispersal of the clays. And if you remember back to our soil texture unit, we in the laboratory, we added salt to the solution to disperse the clay. And that's because of this concept. So we're adding all these very low power positively charged magnets, and that actually causes all the negative magnets to repel from one another and disperse. So sodium causes dispersal, whereas most other cations cause aggregation. So, uh, so flocculation or aggregation, individual particles stick together, they form aggregates or floccules. And these aggregates are big enough that they're not going to really move around in solution very much. And it really forms the basis of soil structure. On the other side, we have dispersion, where the aggregates do not form, or if they're present, they actually get broken up and dispersed. So there's individual particles that are moving around. And if we don't have aggregation, and instead we have dispersion, then water and air and root movement in the soil is inhibited because those dispersed particles start to clog up all the little pores as those particles move around in the soil profile. And this is not a desirable thing for soils. So it makes the soils less productive. There's less aeration, less water movement, harder for roots to move around, and it just causes problems. So the types of cations that are present in the soil really have a big impact on this. So generally, sodium causes dispersion. There are exceptions in some very unique situations, but in the vast majority of cases, if we have a high amount of sodium, then we're going to have clays being dispersed in the soil profile. But if we have cations that are smaller in size and have a lot of charge, like calcium, magnesium, and aluminum, or are just very small in size to begin with, like hydrogen, then those actually cause flocculation because we can squeeze in enough magnets that have enough power in between those clays that there's more of an attraction between the negatively charged colloids, or the clays, and those cations than we have for repulsion forces between two different clays. And so the more charge we can fit in between two clays, the more likely we are to actually get this flocculation. And so in general, the way to remember this is the higher the valence, the better. Because the higher the valence, the more charge we're going to be able to squeeze in between those two negatively charged clays. All right, and moving on to anion exchange. So anion exchange is conceptually the same as cation exchange, except we have anions that are floating around in solution that become absorbed onto positive charges on the colloids. So it follows the same principles of cation exchange. The only thing that's different is we have negatively charged ions and positively charged clays. So the anions are exchanged for equivalent quantities of similarly charged anions. The reactions are reversed, and released anions can be taken up by plants. Anion exchange generally occurs to a higher extent in higher weathered soils. So if we have a mild weathered soil, so most of the soils like we have in the Midwest, those soils have a lot of 2-to-1 type clays with a high CEC. And then as we get more intense, we get less 2-to-1 clays and more 1-to-1 clays, and we end up having a lower CEC. And then once we get really intense weathering, so say in the tropics, then we get a lot more iron oxides and aluminum oxides and less 1-to-1 clays and definitely less 2-to-1 clays. But when we get these oxides, that's really when we get a lot more anion exchange. So the more weathered the soil is, the more anion exchange capacity there will be. The less weathering that has happened, the more likely we are to have 2-to-1 clays and a high CEC. So make sure you review this chart and kind of pay attention to the trends that we see as it associates with kind of a unique situation, but that's our intersphere fluxes. There's also what we call sorption of organic compounds. So what can happen is if we have an organic compound that might not be polar, so it could be a non-polar compound, it can be partitioned into the soil organic matter. So we have these organic compounds that are part of the soil organic matter, and these organic compounds, if there is another chunk that's smaller, another chunk of organic matter that's smaller, that's floating around in solutions, could be an herbicide, Could be an insecticide or some other sort of pesticide, or some sort of compound that was exuded by a microbe or a plant. Those organic compounds can become enveloped and then becomes actually part of the soil organic matter. So this this can happen with nonpolar substances when those nonpolar substances come in contact with a nonpolar section of a bigger compound like you see here. So it's still possible for nonpolar substances to be absorbed, or in this case, sorbed or partitioned into the soil through the organic matter. Generally, clay minerals are coated with water, and so it's really difficult for organic compounds to absorb, especially if those organic compounds are nonpolar. It's difficult for those to absorb onto the clays unless they are either polar themselves or there's something else going on. But yeah, generally, organic compounds won't absorb onto the clays themselves unless they're polar. If those organic compounds are nonpolar, they will become partitioned into the soil organic matter. Now, what can happen is you could have a chunk of organic matter that has a cation on it, and that cation can sort of bridge that organic compound to the clays. So we kind of get some what we call cation bridging to make it so organic compounds can absorb onto the clays. All right, last slide in this unit. I have a couple of review questions for you. So based on the soil pH, which of the following two soils would have the higher anion exchange capacity? And second question, identify the one cation below that in a high enough concentration would cause dispersion. All right, so first question, which soil would have the higher anion exchange capacity? So generally, the more acidic soil we have, the more anion exchange capacity we have. So the answer to this one would be A, the soil with a pH of 5. And then which cation causes dispersion? That is sodium. So the rest of these would cause flocculation, while sodium would cause dispersion.